Today we will see LeetCode problem number 993, and it's called cousins in binary tree. And we will see a solution which will be based on depth first search, and its time complexity is order n, and we will not use any auxiliary space for that. There are other solutions as well where we can use breadth first search, or we can even have this tree replicated locally in the form of the parent and distance from the root of each node. So we will briefly discuss those solutions as well, but we will mainly focus on the depth first search based solution. So first let's understand what is the meaning of cousins in a binary tree. So you see this binary tree, this is a binary tree, every node has at max 2 children. So if you look at 2 and 3, these are siblings. They are at the same level, and we will start our level from root. Root will be at level 0. Next will be level 1. Next will be level 2. So the children of any node are at one level more than the parent node. Now if you consider 2 and 3, are they cousins? No, because they are at the same level. So for cousin we need level should be same and parent different. These are the two conditions. So here level is same, 2 and 3 both are at level 1, but their parent is common, 1. So they are not cousins. So it will be false. Now let's see 2 and 6. Are they cousins? 2's parent is 1, 6's parent is 3. So parent is different, but their levels are also different. Level should be same. So this is again not a pair of cousins. Now let's see 4 and 6. Are they cousins? First condition is are they at same level? Yes, 4 and 6 both are at level 2. Do they have different parent? Looks like, because parent of 4 is 2 and parent of 6 is 3. So both conditions are satisfied. So 4 and 6 are cousins. Now what approach you can take? Let's say you have one single binary tree and it will not change, and you have multiple queries coming in for all such pairs. Are these cousins or not? Are these cousins or not? Let's say thousands and thousands of queries are coming to you based on a single binary tree. Then it would be wise to store the information for each node in a dictionary, which can contain node, and the values can contain level and parent pair. So once you traverse this tree in whatever manner you want, DFS or BFS, you build this map. So now this map has all the nodes and their level and parent info. And then whenever a query comes, this node can have value, integral value. So whenever a query comes, are 2 and 3 cousins? So you will find this value for 2. You will see that for 2 it will be 1, 1. So it's the level and it's the parent. This will be for 2. For 3 it will be 1, 1. So you will fetch these two in constant time and you will check L are same, P are also same, so it's not. Then a query comes 2, 6. So for 2 it will be 1, 1. For 6 it should be, level should be 2, parent should be 3. So you will see that levels are different, so you will return false. So if that is the scenario, that will depend on the use case, what algorithm you follow. So if the algorithm is like that, same binary tree, but multiple queries of this, then you should go for this. So this will be order n time, this building the map, and then all the subsequent queries will take O of 1 time. But if it's given that you will be given a tree and a cousin pair or a node pair n1 and 2, and you will be asked, are they cousins in this tree or not? Every time you get a new tree. So this is T1. Next time you get a different tree, and different node pair. N2 for second example. So if this is the scenario, then you don't need to store these things in a map. You will not make any use of it. This will be used for just one query. So you can save a space here and do DFS, and that would also be linear time. Because if the trees are changing, by storing them, you are not gaining anything. You take ON time to build the map, then O1 time for query. So overall, it will be ON. But if there are multiples of query based on a single tree, then the average time will substantially reduce in this kind of approach. But in our case, looks like the test cases will be tree and node pair both. So each time you will get a different tree. So I thought it would be good to save some space, and we will follow depth first search approach. So what approach we will take? We are given a root node, and we are given two other values, x and y, which denote two nodes in the tree. And we have to return a true or false depending on whether x and y are cousins or not. So what we will do, we know that this is the main function f. So we know that root is at level 0 and its children will be, its two children at max, because it's binary, will be at level 1. So we see if root's left is present, then what we will do, we will compare if any of these, if left is equal to x or y or not, any of these. So if it's left, I will write it as L is equal to x or not. And by this comparison, we are comparing the values. In the code, we will write slightly differently. So is 2 equal to this or not? Let's take concrete example, 4 and 6. So is 2 equal to 6 or not? If it's equal, then we will update some value. We will have one level, dx, dy, and these are holding the level values. Ultimately, we can have -1. We know that -1 level does not exist. It starts from 0. So whenever we find x or y, we will update these values, and duplicates are not allowed. So this should be updated only once. So if we find anything, we will see what is the level of the node that we are comparing. So it will be one more than that, because when we are at a given node, we compare if its left's value is equal to x or not, or its left value is equal to right or not. Similarly for right. So its level will be one more than the level of this. So we will create a function f1 where we will also pass the level. We will pass root, x and y. Then we also pass one level, and for root it will be 0. So these checks we will add here. If root's left is there, we compare if left is equal to x or not. If left is equal to x, what we do, dx equal to d plus 1. So d is the level of current node x, current node r, root. So if we found x, update the dx, also px. One parent we can keep. What are the parents of x and y? So we need 4 variables, dx, dy, px, py. So dx denote the level of x node, x and y are nodes. Dy denotes the level of y node, px denote parent of x node, py denotes parent of y node. Very simple. And when we are traversing this tree, and whenever we find x or y, that is any of these nodes, we update the corresponding level and parent. And its parent will be root. Similarly, we can compare if L is equal to y. And two more things. Right is equal to x and right is equal to y. These are the 4 cases. So whenever we reach any node, we see if its left is equal to x, or left is equal to y, or right is equal to x, or right is equal to y. In all the four cases, the parent will be this node, the current node that which we are visiting at the moment. And their labels dx or dy will be one more than d. So, and ultimately, when we populate all these four values, we return from this function. And in parent, we compare whether dx is equal to dy or not, and px is not equal to py, and we will return accordingly. You can traverse the complete tree, but we can return prematurely if we see that all the four values have been updated. Then we know that we have found both the values somewhere in the middle itself. So we don't need to traverse the tree further. So let's write the code for this approach. So first I will write it in C++. So each cousins is the main function. I will create one function void, and we will call it parent and depth, because we will be calculating the parent and depth of these x and y nodes. And we will need these three here. And additionally, we will pass a few values by reference: dx, dy, px. And you see that here parent I am taking as integer because these nodes have a value, integer values, and duplicates are not there. So we can even compare their values. And what else we need? We also need one label. Let's call it D. And here we will initialize those values. Int px equal to 0, py equal to 0, int dx equal to -1, int dy equal to -1. So these are uninitialized, and we will get to know this from the value, because -1 level does not exist in a tree. We are starting from level 0. So it can be 0 or more. And then we will call this function parent and depth root x, y, level for root is 0, then dx. First we pass d, then p, dx, dy, px, py. And then we will return dx should be equal to dy and px should not be equal to py. So this will return true when both these conditions are true. Now let's fill this main function, the auxiliary function that will do the main backend job. So if root is null, then return. If root left, that is left child exists, then we compare if left is equal to either x or y. Then the parent of x will be this root, and label of x will be d plus 1. The label of current node d plus 1. Else if py will be root val and dy equal to d plus 1. And we will do the same thing for right. And then what we need to check, if both x and y are found, we don't need to traverse further, just return. So if dx not equal to -1 and dy not equal to -1, then return. We have found both of them. Otherwise, we will continue our search. So d will be 1 more than d because we are doing it for its children now. Left and right. And these should remain same. So that's it. Let's try. It works for this example. Let's submit and see if it passes all the test cases. And the solution is accepted in C++. Now we will do the same thing in Java and then Python. The logic is very simple. It should be clear. It's exactly what we saw in the slide, the explanation. So here we will use atomic integer to pass it by value, pass it by reference, sorry. Otherwise, if we pass int, it will be passed as value. And this should remain same. Then you can also put these dx, dy, px, py as a member variable of this class. That should also work. And if root equal to null, return not equal to null. Tx is atomic, so we cannot assign it integer. We will need to set it. And dx dot set d plus 1. So let's try it. And it's correct, so let's submit. So we got some wrong answer. Output is false. Okay, maybe due to this dx.get. So let's copy this test case. We will run first and then run on this. False, true, false, true. Now it matches, at least for that test case. Let's submit. So in the previous case, if we did not compare this get, it was always giving false because dx, dy are two different atomic integers. So it will always be false and our answer will always be false. And the first test case, the answer was false. That's why it was matching. But for other test cases, it was failing. Now it works in Java and has been accepted. We will now write the same thing in Python. Exact same logic, just 3 different languages. And here we will put it in self itself. Let's copy this thing. That should be much easier. So that's it. Let's see if it works. And it gives correct result for both these test cases. So let's submit the solution in Python 3. And the solution is accepted in Python as well.